Now we're going to charge a capacitor through a resistor. We're going to put capacitors and resistors in the same circuit with a battery. And to be able to control when it happens, I'm going to put a switch there, like that. So here's R, here's C, there's a switch, EMF. Okay, so what's going to happen? When there was no resistor, we would just say close the switch and charge will immediately flow onto the capacitor, and we know how much charge will flow, EMF times C. You get charge on this side, negative charge on that side, we know what's going on. And we say it happens instantly. But now we have a resistor here that will resist it happening instantly, and that'll slow the process down. So this is an RC circuit. And what's interesting about RC circuits is nothing happens instantly. Things change in time. To describe that in detail is a little bit long. I'm going to post the videos of me describing it for 102 in 2013. And you can watch that if you want all the math. But you got to set up a differential equation with Kirchhoff's loop rule. You got to solve the differential equation, yada yada. It's not that hard. You could do it. But in our current circumstance, I think I'm just going to quote you the result, and we'll talk physically about the result a little bit. Okay, so if you close that switch, we're going to charge the capacitor through the resistor. So let's look at the charge, which is now a function of time. Okay, so the equation for the charge is the EMF times the capacitance times 1 minus e to the minus t over RC. Now the exponential, you might say, why is there an exponential? It's because when you solve the differential equation, you have to integrate something, and it has the form dx over x. And the integral of dx over x is natural log of x. And then you mess around to get from a natural log to an exponent. So that's why there's an exponent shows up. And watch the other videos if you want to see the whole thing. If you were to plot this function, 1 minus e to the minus something looks like this. So if you plot this function at time equals 0, then it's going to be what? E to the 0 is 1. 1 minus 1 is 0. It's going to be 0 at time equals 0. And it grows kind of like that. But eventually it stops growing, because if we make this really big, e to the something really big, e to the minus something big is 1 over e to the something big, which is 1 over something big, which is 0. So eventually this thing is shrinking down to 0, exponential decay towards 0. 1 minus 0, now it's a constant, constant, constant. So basically this thing approaches this magic value EC, which you recognize as it being fully charged. So that is the charge as a function of time on that capacitor. Okay, so exponential approaching the saturating value. And you can even tell it's an exponential. It's 1 minus an exponential. If you look, see, that looks like an exponential decay. Just 1 minus exponential decay. We could also ask, what is the current through the resistor? Well, if this is charging, if the current that flows is charging that capacitor, then we know that I is dq dt, and we can get the current behavior by just taking the derivative of this, which we can do real quick. It's two terms, EC times 1 is just a constant, so the derivative of that is 0. So we're really taking the derivative of minus EC e to the minus t over RC. So that's C. So that, well, the constant part was minus EMF times C. And then when you take the derivative of an exponent with respect to something, you take the derivative of the part up here, which is minus 1 over RC. And then you just write the exponent again. Right, so we can simplify that a bit. The two negatives cancel, the capacitors cancel, and you get equals the EMF over R, e to the minus t over RC. So you get exponential decay. So I'll plot that a little smaller. So here's the current through the resistor as a function of time. It starts at time 0, e to the 0 is 1. It starts at the EMF over R, and then it just decays away towards 0. Really big time, that goes to 0. Exponential, so this sort of growth to a limiting value for the charge, exponential decay for the current. Right? And these are the important formulas that you would use in problems. The current is exponential decay. But now let's talk about them physically a bit and see if it makes sense. So one thing interesting about them is they're both limiting, or they're starting at sort of the value you would get with the other part missing. If this capacitor weren't here, the current you would get, according to Ohm's law, is EMF equals IR, would be the EMF over the resistance. So it actually starts out at that value. This initial current is like the capacitor's not even there. And then at long times, it's like the resistor isn't there. Because at long times we've charged up the capacitor and there's no current flow left. So at long times you do just get the EMF times the capacitance. But the reason it's going through this transition is that at the very beginning, the whole EMF shows up across the resistor because the capacitor has no charge. So the delta, the potential drop across the capacitor at the beginning is 0. So all the potential drop occurs here. So you get a big current. And then in time, as you charge up the capacitor, more and more of your battery's EMF starts to show up across the capacitor and less across the resistor. So as that happens, less and less across the resistor means less and less current. More and more across the capacitor means more and more charge. So that's why they're both exponential, but they're sort of complementary to each other. So this is what you need to physically understand and the equations you need to be able to use. We just aren't going to bother to derive them. And the one last thing I'll add is you'll hear about the time constant. So the time constant for a circuit like this is just a name for the exponential decay rate, which is right there. The time constant is tau is RC. Okay. So it's a little bit confusing. No, it's not confusing. Yeah, tau is RC because that's in seconds. So remember that anytime you have an exponential of something, this has to have no units. So time is in seconds and RC is in seconds. If you think about it, RC is in seconds. If you start messing with volts and coulombs and currents, you find that, yeah, the unit of RC is seconds. So in a problem, you might be given tau, and it just means the product of the RC, and it tells you how fast it decays.